Hello everyone. In this video, you will learn how to design an AXI4-Stream transmitter in Verilog. We will first discuss the AXI4-Stream Protocol, then we will implement it in a complete design example. After that, we will run the design in real time using Vivado and Vitis. Once you understand the example, you can use the same idea to make other custom IP blocks transmit data with AXI4-Stream. This is an important skill because AXI4-Stream is used in many FPGA-based system-on-chip projects. For example, in the project where we run a fast Fourier transform on an FPGA, one of the IP blocks uses AXI4-Stream. Alright, let's get started. In FPGA-based system-on-chip design, AXI4-Stream is a communication protocol used to move data from one IP block to another. AXI4-Stream is used for one-way data transfer, meaning there is a transmitter IP block that sends data and a receiver IP block that receives data. In this video, we will learn how to make an IP block transmit data with AXI4-Stream. In the next video, we will learn how to make an IP block store data it receives from an incoming AXI4-Stream. AXI4-Lite allows an IP block to read or write specific values at specific addresses. This is great for control, but bad for speed when large amounts of data need to be transferred. It is slow because moving one value with an AXI4-Lite write command requires multiple clock cycles across 3 separate phases. There is an address phase, a data phase, and a response phase. AXI4-Stream allows an IP block to move data continuously. This is great for speed because a new value can be transferred every clock cycle. The trade-off is that the AXI4-Stream has no address bus, so extra logic is needed to control where the data is stored. The figures below show the speed difference directly. AXI4-Lite transfers one value after a multi-cycle write command, while AXI4-Stream can transfer 8 values in that same time period. When a Verilog module transmits a list of numbers using AXI4-Stream, the Verilog module uses the pink signal as an input and the green signals as outputs. It does so by using the following rules. First, the initial conditions must be set where the outputs are all 0. Second, when a transmission begins, the T-data output is updated with the first value to be sent, and the T-valid output is driven high. Third, if T-valid and T-ready are not both high, then the outputs remain constant. Fourth, if T-valid and T-ready are both high, the module updates T-data with the next value. If the next value is the final value, T-last also is driven high. Fifth, if T-valid and T-ready are both high while the final value has already been sent, then the module resets to the initial conditions. We will design a Verilog module that receives an AXI4-Lite write command. If the correct write command is received, the module will shift out 16 pre-initialized values using an AXI4-Stream bus. After we have designed and packaged our IP, we will use it in the following real-time demonstration. First, an AXI4-Lite write command is sent to the stream IP using the correct address and data value. After the write command has been sent, the stream is generated, causing 16 pre-initialized values to be sent out serially into a FIFO IP block. The processor pulls the FIFO through its S-AXI interface until the FIFO reports that a complete AXI4-Stream packet has been received. After the FIFO reports that the AXI4-Stream transfer is complete, the processor reads the FIFO contents and sends the values out through UART. After the FIFO contents are read out, the Vitis serial terminal should display the same 16 values originally stored in the AXI4-Stream slave IP block. If those values appear correctly, then the full system worked as intended. This here is the Verilog code. The Verilog module was made by modifying the start pulse IP from the previous lesson on AXI4-Lite write commands. The main changes are that AXI4-Stream ports were added, the AXI4-Lite write ports were renamed with the S-AXI prefix, and the AXI4-Stream ports were named with the M-axis prefix. Those prefixes are needed because they help the IP packager recognize the signals as belonging to an AXI bus. The only part of the Verilog module that has new logic is lines 184 to 298. This is where we add the AXI4-Stream transmission logic. Because of that, only those lines will be explained. The previous lesson on AXI4-Lite write commands covers the other lines. On lines 184 to 209, the AXI4-Stream registers are defined, and the 16 memory values are initialized. These are the 16 predefined values that will be shifted out over the AXI4-Stream bus. On lines 211 to 296, we implement the 5 steps needed to shift out the data using AXI4-Stream. The first step is to enforce the initial conditions during reset and while the module is idle. T-data, T-valid, and T-last are cleared to 0, and the stream index is reset to 0. This ensures that the AXI4-Stream output starts from a clean idle state before any transfer begins. The second step is to start the stream. When the AXI4-Lite write command produces the start pulse, the module loads the first predefined value into T-data, drives T-valid high, keeps T-last low, and moves into the send state. The third step is to wait for the receiver. In AXI4-Stream, data only transfers when T-valid and T-ready are both high. If that condition is not met, the module holds T-data, T-valid, T-last, and the stream index unchanged. The fourth step handles normal transfers. When T-valid and T-ready are both high, the receiver accepts the current T-data value. The transmitter then loads the next value into T-data. If that next value is the last value in the list, T-last is driven high with it. The fifth step happens after the last value has already been accepted. At that point, the transmitter is finished, so it clears T-valid and T-last, resets the index, and returns to idle. This is the Vivado block diagram for the demo. It uses the same MicroBlaze setup from the previous lessons, but the peripheral blocks have been changed to the AXI4-Stream transmitter IP, the AXI-Stream FIFO, and the UART, and ILA is also connected to the start pulse output. I will not go through the full block design setup because it is the same one from the previous lessons, just with the modified peripheral blocks. The main thing to check is the address assignment. After validating the design, open the address editor, find the base address assigned to the custom stream IP, and make sure the IP parameter and Vitis code use that same address. After that, generate the HDL wrapper, generate the bitstream, export the hardware with the bitstream included, program the FPGA, and move into Vitis. To run the demonstration, open Vitis in a new workspace directory. Create a new application project, select the exported hardware file, name the project, and create a blank C application. After the project is created, add a main.c file, connect the Vitis serial terminal to the board, and set up a run configuration. Then paste in the demo code and build the project. The demonstration code will not be explained in detail because the main focus of this lesson is the Verilog IP block. The code will be provided with the course files, so you can study it separately if you want. However, you may need to modify the code if your address assignments are different. To check your addresses, open the xparameters.h file. This file will help you rewrite the Vitis code to make it work for your addresses. The reason is because it tells you what addresses actually got assigned to the custom stream IP, the FIFO, and the UART. After the code builds successfully, arm the Vivado ILA and run the Vitis program. You should see the ILA capture the start pulse, and the serial terminal should print out the 16 pre-initialized values that were streamed into the FIFO. Alright, so there you have it. You have now finished designing your first piece of custom IP that uses an AXI4-Stream bus to transmit data. If you understood how this lesson worked, then you are ready to add AXI4-Stream transmission to other Verilog modules, because the protocol itself never changes. In the next video, we are going to design an AXI4-Stream receiver in Verilog. Before watching that video, I recommend attempting the problem yourself, then watching the video to check your solution. The problem we will solve in the next video is shown here. Alright, that's all for now. Looking forward to seeing you in the next one.